So the title of my talk is an alternative to firewalls. And fortunately, Steve Giddings sent me an email that said yes. So, I mean, we're basically done. There is an alternative. Unfortunately, I haven't figured it out. So.
Well, as I pointed out, it's better if they attack you than me. So.
This is an excruciating talk to give because I really have no idea why I'm here and what for, because you guys know all about firewalls and I haven't gotten rid of them. And also it's just not clear what level to aim at, so I'm just going to start super basic, despite the fact that you're all experts, and try to give you my angle on the problem and some of the things that I've tried that don't work so far. So let's start with some facts about quantum mechanics. So one thing that I want to emphasize is that I'm not completely sure how much modifying effective field theory by itself would help. It seems to me that quantum mechanics would almost have to be on the line, which is bad. So let's start with some bipartite quantum system. So the Hilbert space is this. And I'm going to introduce notation of this type. So NA is the log of the dimension of the Hilbert space A. Basically the number of degrees of freedom. SA is going to be minus trace rho A log rho A, where something like rho A is obtained from the larger system by a partial trace. Now let's assume right now that rho AB is pure. In that case, I'm going to give the following definition for maximal entanglement. Okay, maximal entanglement means SA equals NA. Okay, or another way of stating this is that rho A is the unit matrix divided by NA. So this notion of maximal entanglement is going to be very useful. To have maximal entanglement in this situation, I would need that NB is greater than or equal to NA. Otherwise, it can't happen.
Wait a minute, you defined NA as the log of the dimension?
Yeah. That's right. Otherwise, I would have, yeah.
So how come the density matrix is 1 over N?
Thank you. Thank you very much. Good. And then, a classic example would be if I have 2 qubits, this would be a product state. And then, of course, this would be a maximally entangled state if correctly normalized. And then this would be something in between.
And what do you do for systems like, say, that we're accustomed to, like hydrogen?
Like hydrogen?
Yeah, which has infinite dimensional numbers.
I keep my mouth shut about them.
So what? Are we discussing just single qubits?
Well, I think that I can discuss what I want to discuss in this framework of finite dimensional Hilbert spaces, but maybe we should come back to it when we get. I mean, right now I'm just trying to make not incorrect statements about finite dimensional Hilbert spaces.
I think you put it in a box and cut off the energy.
It's great to do in gravity.
Yeah. Okay, so here in general, SA can be between 0 and log 2, and here it's really in between, for example. Okay, so much for maximal entanglement. Now, the other concept that's really important for the by now legendary argument of amps is the monogamy of entanglement. Okay, so let's say we have 3 qubits. Okay, and let's suppose that A and B are in this state. maximally entangled pure state. Okay. Is it possible to write down a state for the ABC system, for the whole system, such that B is also entangled with C? Let's just, to make it particularly crass, let's say same kind of state for B and C, maximally entangled. And the answer is no. Okay, so if we have this, you can't, in fact, have any entanglement at all. You can't even have any correlations between B and C if A, B are in this state. And there's a sort of intuitive, well, okay, the best intuitive explanation of this that I can come up with is if you think of this as some sort of EPR pair, and now you're trying to make another EPR pair that B is again a member of. What you could do is take the first EPR pair and project it onto 0. And you could take the second EPR pair and project the C bit onto whatever, 0 plus 1 over square root of 2. But either of those things will put B in a definite state. And those two definite states are not the same. Indeed, again, as here we have maximal entanglement. So basically what I do to A, whatever I project A on, completely controls B. So there can't possibly be any other object that is in any way correlated with B. Okay, so that's the statement. And the formal reason, at least some powerful statement that implies the special examples I've discussed, is strong subadditivity. Which is the statement that SABC plus SB, well, there's various equivalent statements of this, is less than or equal to SAB plus SBC. So just to go for the particularly extreme example, if I wanted this to be a pure maximally entangled state, then this is 0. This is a pure maximally entangled state, so this is also 0. But because B is maximally entangled, SB is not 0, there's already a contradiction. Good. So far it's just, actually it's going to continue just being quantum mechanics. Then there's this beautiful result by Page on the entropy of a subsystem. I'm not trying to be, the AMPS paper is written in a way where the assumptions are trying to be as minimal as possible. They don't actually really need Page's result. But since in the end they don't need it and it's easiest to illustrate the problem by using it, let me just use it. And clearly the argument is not going to be that Page's result is somehow wrong. So again, we're going to go back to this bipartite system. And we're going to assume again that NA is less than or equal to NB. Yes?
Just to be clear, I mean, if you're not maximally entangled, can B have some entanglement with A and some entanglement with C and not violate strong subadditivity?
Well, you can never have. You clearly you can't. So if this is pure, and you want B to have some entanglement, then this can't also be pure. I mean. That's one of many true statements we derive from this.
There are limits. Yeah.
But you can trade entanglement between two. Yeah. Yeah.
Well, you could have some mutual entanglement. You could have 0A, 0B, 0C plus 1A, 1B, 1C, and everything.
Everything's
So a very simple way of thinking about it is think of B itself as a bipartite system. Maybe it's 2 qubits, and you can entangle one qubit with one system and the other with the other. That would be a very simple example of splitting entanglements. Yeah.
One thing you could say is if A and B are more strongly correlated than is allowed classically, then B and C must be less strongly entangled than is allowed classically by a corresponding amount. To make that precise with a statement called weak monotonicity, this is just a sort of rephrasing. Relates closely connected to strong subadditivity.
So I want the full AB system to be in a typical, in the Haar average sense, pure state. So this rho AB is, again, it's a pure state. Let's write it as. And what Page showed is that in this case, SA is, to an extremely good approximation, given by maximum entropy that A can have, given the size of its Hilbert space, minus a small correction, which is at most a half, and is exponentially small if the Hilbert spaces differ a lot in dimension. So for all practical purposes in this talk, when I'm going to look at less than half of a system, I'm going to treat it as maximally entangled. The distinction, this small correction will not be important. Another way of saying this is that if you define the information that you get out about how much you learn about which pure state this is, a nice way of quantifying that is So you're trying to figure out what state is the big system in. You're looking at less than half of the big system. The statement is you basically don't get any information. You don't even get a single bit of information. You can't narrow down at all what state it's in. Of course, in the pure state case, SA is the same thing as SB. And so the thing that you could have in mind, again, so far we're just doing quantum mechanics. So imagine that you have a bunch of spins, but they're not in what I'm drawing here, some product state, but really a typical state, which would be a superposition of these things. And now you go and you look at these spins. You measure them. You learn virtually nothing about.
So what does typical mean?
Haar average. So basically he takes
average over what?
Over the Hilbert space.
Or UN.
Haar average is over some group. What is
the group associated with the Hilbert space? So it has a dimension.
The
And
space is
it's,
finite,
yeah.
you have a finite unitary group acting on it. You average over that.
Why is that typical?
That's the definition of Page.
Yeah. What's the
Well,
physics? I mean, I could define lots of measures. I could put in some action that you infer, I think, is also.
Again, it's saying you have no information on the Hilbert space other than the inner product in the Hilbert space, and you pick at random by classifying your states.
Yeah, so for example, there's no Hamiltonian that's being used here. There's no Hamiltonian. So it's really just a Hilbert space. That's the only structure that's involved here. Maybe there are other natural measures one could define on it for which such a result would not hold, but I'm not aware of that. I mean, you need to give some. I guess the idea is that you want some definition.
We tend to think of physics.
Yeah.
We usually have more other measures other than averaging over Hilbert space, which is a pretty unusual. If you actually think about it, Preskel has a wonderful argument that most states for physical systems,
Yeah.
the vast majority of states are not accessible by what we would call physical operations, local operations.
Wait, what about thermal equilibrium? I mean, there we assume an ensemble control states are populated equal probability.
Yeah.
No.
I think I'm gonna.
First of all, we have constant finite energy.
The thing is this. Suppose that this result of Page was not correct for some reason like this. It would still be true that the AMS argument goes through, because it only relies on strong subadditivity.
You're assuming a little bit too much expertise in the audience and trying to formalize in general terms, assuming you just have qubits and not even one harmonic oscillator. So what is an argument that some of us don't know, aren't authors of the paper. In trying to put this in a very formal, so that only magicians could object. Rigor, I'm losing the connection.
Yeah, good. I mean, actually, my goal here was to have less rigor than these guys. But I'll come. Okay, let me insert their argument that gets around page at the appropriate time when I get to the black holes, because that involves specifics about unitarity and Hawking radiation, and so let me get to that when I have that. But let me just say one more thing here at the not logician level that may help make this more intuitively plausible. What this statement is basically saying is that if you look at less than half of a system, the larger half can act to good approximation as a heat bath. This is a thermal. It's essentially a thermal. It's a very mixed state.
Yeah, except this tends to conflict with. You remember Pascal talking about that at Brussels? Did in real physical systems with what we think of as a natural basis, which tends to be a local basis, you never, in a sense, most of Hilbert space is inaccessible. There is no ergodic mixing.
That would be so. I would be delighted if it turned out that black holes somehow managed to exploit that to get around this problem. But as I'll argue, you don't actually need the entropy of a subsystem to be as large as advocated by Page. But David, I think I need to. I mean, precisely because this is not central to AMS, I don't think it would be very useful for us to spend too much time on it.
But whatever state you end up in, if you pick a generic basis, the kind of basis we typically work with, say if we're looking at individual particles in this room,
we don't pick generic bases. We always pick local bases. I don't know anybody who picks something bases that aren't products, something close to product states.
Well, if you don't pick something that's adapted to the exact Hamiltonian, then you're going to have something that's kind of random. It'll look a lot like this.
Well, we seem to be getting a little bit ahead of ourselves because we haven't actually said yet how he's going to be using this. So maybe we could hold our fire and object again once this becomes more than just a mathematical statement.
I'm having a great time because I would love for nothing more than Firewalls to be wrong. So please shoot me down. Okay, so let me say for the first time something that's not just quantum mechanics but field theory about the vacuum, something you also all know. Let's look at the Minkowski vacuum in the funny Rindler way. There's a left and right Rindler wedge, and as we know very well from Phil Unruh, I'm going to drop some normalization factors because this is messy enough. The vacuum can be written as a bunch of entangled modes on the left and on the right. So
I have a system that contains described by H.A. Douglas. If H.A. you lose them, the larger here, the smaller here. I lose more. That's bullshit.
kids. So, okay, so all that we do here, right, is we build modes with support on the right. We have modes with support on the left. We build Fock spaces on top of each of these, and we write the usual Minkowski vacuum, which is annihilated by all the annihilation operators associated with the Minkowski modes, with the usual modes. We write it in terms of the Fock spaces that are built on these Rindler modes. And we find that this is, we have some very high degree of entanglement here. This is not really maximal entanglement. The right-hand density matrix is, so the density matrix in the right wedge is just thermal. So the temperature is 1/2 pi. But of course, what this means is that if you're looking at states with Rindler energy of order the temperature or less, those are very highly entangled. The coefficients in the Schmidt bases are order 1. They're not 1, but they're order 1, so they're very highly entangled. And intuitively, those are modes which, so for example, what's not very highly entangled is some wave packet here with a wave packet there. The wave packet is small compared to its distance from the Rindler horizon. But what is very highly entangled is a wave packet whose separation from the horizon is of the same order as its size. So these guys are partnered up. There's a longer wavelength one. They're all partnered up in this way. Okay, so a very similar analysis applies to black hole horizons. Let's consider this to be part of a black hole horizon, say. And again, at short distances compared to the Schwarzschild radius, this is approximately Minkowski space, and you can again write such a decomposition into modes inside and outside, and it'll look very similar in the limit where you're close to the horizon. And moreover, the Hawking quanta that arrive at infinity, if you trace them back, this is just geometric optics. If you trace them back to near the horizon, they become precisely these kind of wave packets that are close to the horizon and of the same separation. In fact, that they sort of fall into lockstep as they enter the near horizon zone, less than 1 Schwarzschild radius away from the horizon. They blue shift, and just as you run back, they blue shift in just such a way that their separation from the horizon is always comparable to their wavelength. For typical Hawking quanta, yeah.
So, I mean, I've heard this analogy a million times, but
Yeah.
I mean, I think it clearly applies near the bifurcation point of the horizon. But now we're going to be interested in maybe a black hole forming from collapse, stuff throwing in later time.
Yeah.
So we need to go up the horizon and look at correlations between modes inside the horizon and outside,
Right.
away from the bifurcation point. And then the left Rindler wedge is sort of not the relevant place to correlate. I mean, you're not correlating left Rindler modes, it appears. I mean,
Well, evolution into the upper.
I would have said, let me just cut this piece of space-time out.
Yeah.
And as long as it's very much smaller than RS in all directions.
But you don't have that point. That's removed by the falling matter. But that's okay.
Which
you can
point?
Look at correlations. The point.
This was not supposed to be the bifurcation point. Oh, I'm sorry.
Yeah.
I'm sorry. This is not the bifurcation point. I'm just drawing that point here. This is the point where somebody falls through.
Yeah. Okay. Then it's okay.
Yeah. This is the point where somebody falls through, and I'm just arguing that this should be like flat space. I mean, because that's the debate. Right, that's the question. Is this going to look like flat space? If it looks like flat space on scale smaller than RS, yeah, the picture was confusing. I'm just putting a Rindler wedge with one. This agrees with the horizon, and this is set by where I'm going to fall through.
I see. So in fact, the Rindler killing field has nothing to do with the time translation killing field of any black hole space-time.
No.
It's just some.
I'm just trying to get from Unruh to. I'm just trying to place Unruh here near the horizon. That's all. Yeah. And of course, this sort of calculation is the basis of Hawking's calculation. So now we can put it all together, and I'm going to ask David to bear with me while I do use this page argument, and then we can come back to why it's not necessary. But here's the scene, and so we have a star here that made some black hole. It was in some pure state, and okay. We're going to have an infalling observer, Alice. Okay, and we have her friend Bob, who stays out here near infinity. And so there's a particular time here.
Before you, as long as you're drawing these pictures with observers, could you also describe how you're constructing the Hilbert space?
Of the observers?
You're talking about pure states. I'd like to know what the Hilbert space is.
Yeah,
approximately.
Yeah, so let me introduce the systems whose Hilbert spaces will be considered. I haven't yet done that.
No, but I'm really interested in.
Oh.
So Hilbert spaces, are you need some basis, and in this context, you need some kind of hypersurface in which you're going to define a basis. Mm-hmm. So could you do that as you go along, so we know what we're talking about? You talk about states that exist in some Hilbert space. What is approximately the definition of that?
You're asking about this state?
Yeah, for example, that's
Okay.
in a Hilbert space.
This
and
could be the
what is
Hilbert
your
space
model of the Hilbert space.
Could be the
Say
Hilbert
a
space
product
of a star.
I don't know that either.
You
But
could do-
I want the question about global characteristics here, right? And two sets of observers. I'd like to know approximately how you're thinking in this picture.
Well, maybe you'll allow me to
Um,
introduce the physical systems
what?
that are going to be relevant
You
for the
introduce
argument.
a state which exists in some Hilbert space.
Yeah, the only thing I'm going to use about this state is that I want a pure state
You're going to have states
psi to come out over
there,
here.
and states here, and I want to know what H is. Those are vectors. Those are states in a
Yeah.
Hilbert space.
Yeah.
What is your
If
very
I-
crude approximation to what this Hilbert space is?
But by the way,
Do you
there's
believe
a
that there
very
is-
sharp way of describing it in the two-dimensional models, and then you can come quite close to that in the higher dimensional case.
I just want to know what is.
I'm sorry, but I think this is.
The
I
Hilbert
think
space could be approximately a product of effective field theory Hilbert spaces at points along some hypersurface. What I'm really asking is, where's the hypersurface you're going to draw on to define the Hilbert space?
Take a surface at very early time.
There are many surfaces.
Yeah, to define this Hilbert space. Here's a surface.
That's a surface on the whole
Yeah,
space.
we can extend it. It won't be important because the system here is well localized.
Okay. So this is the Hilbert space which you're going to define.
Right.
States.
Right.
That's your
Right.
slice.
And then there's some Hilbert space here where I have on this slice where I have the Hawking radiation and no more black hole. And if I believe in unitarity, then this is basically the same state. I'm going to suppress writing down the
So
S.
Hilbert spaces, this change, quantum mechanics, states change, operators change.
If I collapse, I don't know, carbon and make coal here and it evaporates out to infinity, I mean, are we going to worry about that?
In this case, absolutely. Yeah. Does the
I mean, but you'd have to tell me more than be precise about defining the Hilbert space. I mean, where is the...
You're going to make
where are we
an
gonna-
argument you're going to make a
Yeah.
quantum mechanical
Yeah.
argument. I just want to know what you're talking about. So far, you've been talking about 2 qubit, 3 qubits. And
Yeah, now I'm talking, I've switched to field theory.
Geometry.
Yeah. So I've discussed Hilbert spaces here. It's going to be important to have some Hilbert spaces for modes inside and outside the horizon.
That's part of the same Hilbert space. And the Hilbert space you're talking about is a direct product of those?
Yeah. So the part of the Hilbert space that I care about is the subspace of highly entangled modes. I don't necessarily care about all of the modes of the field theory. I care about the highly entangled ones, and that's the ones I'm going to focus on. But I can make the argument using those. So
But just to say a few more words, again, the two-dimensional case makes it very explicit with the two-dimensional black holes. So you can, look at free bosons moving in a black hole background, and you can start out with, say, a slice that covers the whole space-time in the vacuum, say, and then you can look at that state and say, re-express it in terms of modes that are localized on one side or the other of the horizon. You can choose a basis like that, and then you get this kind of formula, just like the Unruh formula, where you have the corresponding excitations inside and outside. And the qubit model story is kind of a coarse graining or an abstraction of that, where you really throw away a lot of the extra stuff, but you can really make it all pretty precise.
I just want to see what.
Can I raise another? I mean, I guess our job here is to try to ask as many questions as possible to try to find loopholes and
Exactly.
the inevitable
Yes.
conclusion
Yes.
that you're going
Yes.
to end up
Yes.
saying that they're
Yes.
right. So,
But it's not inevitable.
I hope it's evitable.
I mean, are you worried about the fact that gravity is being treated so classically here, and that you're drawing the same null surface for the horizon that we do in classical GR, and not putting in quantum fluctuations?
We should worry about everything. I don't know how to translate that worry into, into a specific breakdown of the argument. I don't see how it's important to the argument, that, how it's going to change it to include such corrections. But
as far as I can tell, the argument shows that it is important.
Something.
Well,
How can you possibly make that?
I think the classical limit is very, it might even be discontinuous in a sense.
If you go back to the original Hawking calculation for information loss, when you say there's a problem there, I mean, it's roughly this. He's living in roughly the same Hilbert space as Hawking would have used, right? I mean, right?
Well, we know there's a problem with the argument for information
That's
loss
my
because we don't
classical
believe information is lost.
Right. Good. So. Yes.
Yes.
And so.
yeah. So because we don't believe
But
that
you don't know where it breaks down. He's going to tell you where it breaks down.
Some of us have argued for where it breaks down.
Okay, so the systems to which I believe I can associate a Hilbert space analogous to I would have done for the piece of coal, but again, maybe there are subtleties, are so R is defined. First of all, let me emphasize that the timescales here are enormous compared to formation timescales. So Alice falls in at some time that is just to make the argument sharp, larger than half the evaporation time. So it's set by m cubed in Planck units, and the precise time of her infall divides the Hawking radiation that's eventually going to come out into two subsystems. But it's important to understand, while I can think of one of them as the state of the black hole that she falls into, it's important to understand that I can think of both of them, if I choose to, in very harmless field theory terms. Eventually, the whole black hole is going to evaporate. I have a big cloud out there. This cloud looks like this. It moves out. It's some shell of thick shell of radiation of width m cubed. And I'm just going to divide that shell into two pieces. The part that came out after Alice fell in and the part that came out before Alice fell in.
There's
And
another way of phrasing Gary's question. Maybe you could answer it now.
Good.
Is we know already, right? And these authors know as well. Information is not violated.
Yeah, that's going to be.
Hawking was essentially wrong.
Right.
Got to the wrong conclusion that the classical solution to general relativity, which has a horizon that you're talking about, does not describe, is not a pure state.
Yeah.
Right?
So then there must be firewalls.
There mustn't be firewalls. It's just the state you're talking about. But you're going to go through an argument which is based on saying, okay, we have this background.
Maybe I can actually go through the argument.
Let me go through. There's a background metric which we treat classically.
Yeah.
And then we have pure states falling into it. And
It's fine to include corrections to this. The back reaction is not
There's no
important.
correction to it. I mean, those are not treatable by perturbative corrections to
Nobody has-
classical gravity.
Nobody has found a way of sort of saving us by looking at small fluctuations of the horizon.
Indeed,
People
but
have
we
tried.
know it's wrong. So
Yeah,
why is
so
it
what do
right
we-
to think
what do we
about
need
it
to change?
since nobody's thought about it?
I think it would really.
Why is it right?
I want to have this discussion, Dave. I really do want to have discussion. Again, nobody would be happier if we can get rid of the damn things. But I think the discussion would be much sharpened if you first let me go through the argument and we then pounce on it. Okay, you don't have
Go
to.
ahead.
I will accept that you don't believe every sentence I'm saying, but let me still say them, and then
No, it's a
let's.
starting point.
Like I said, better that you be attacked.
It's fine. So let
Gary
me.
said it's a starting point.
Let me get from the starting point to the end point, and then it'll be clearer which parts of the starting point are important to attack. And again, I'm happy to see them fall. Okay. So the thing that I want to do is, first of all, I'm going to impose unitarity. Okay. So this thing here, as a whole, as measured by Bob at infinity, is the same state as psi. That's one assumption. I mean, some S matrix acting on psi, but let's work in kind of Heisenberg picture. So it's a pure state. It's a pure state. Now we're going to divide this pure state into two pieces. This is just a Hawking cloud right now. There's a smaller piece which I'm going to call R prime, which is actually, I drew this the wrong way. I guess the late Hawking radiation is R prime. The early, that's supposed to be the smaller piece. And there's a bigger piece R, which is the radiation that came out before Alice fell in. And we're going to evolve R prime back to the near horizon zone, by which I mean a region no more than about 1 Schwarzschild radius away from the actual horizon. That's a region where we would think that effective field theory should be valid, semi-classical gravity should be under control. All of these things, one should triple check. Okay, so in this case, what we end up with is the smaller of two subsystems right here near the zone, the larger one out here near infinity. Using right now my shortcut of Page's result, and coming back to the general case later, this subsystem here is almost completely entangled with this subsystem. It is purified by the older Hawking radiation. That means that I just cannot write down a quantum state here that corresponds to the infalling vacuum. If I have an infalling observer who wants on some scale that's large compared to the Planck scale, but small compared to the Schwarzschild radius, wants to see empty Minkowski space, just by the monogamy of entanglement, I can't write this state down. I cannot have any entanglement of B with the partner modes A in here. So the problem is, let me denote entanglement like this. Equivalence principle demands that B is entangled with A, and you can't have both. And effective field theory was also used in transporting R prime back to B. Those are the three essential assumptions that go into this argument. Now, if we forget about Page, then you have to go back to the strong subadditivity inequality, and you have to use the fact that unitarity implies that at some point the information has to come back out, which means that there has to come a point when the entropy of the Hawking radiation starts to decrease. Okay, so then you break up the Hawking radiation into the radiation you already have, and the next bit that's about to come out, and you have to have this be true.
Sorry, rephrase that. At some point,
so in order,
information has to start coming out.
Yeah. So
the information where?
In the Hawking radiation. So in the end, we're not negotiating unitarity.
Well,
so
Hawking radiation, or by which you mean what is observed by an observer?
Yeah, at infinity, exactly.
That's always a pure state, right? So,
well, not while the black hole hasn't fully evaporated.
Right.
So the argument is just that.
Again, this requires you telling me what the Hilbert space is.
This is just the Hilbert space at infinity. You stand back, you watch the Hawking particles come out.
I'm off at infinity.
Yeah.
Okay.
And then, yes.
But then I have a pure state, right?
No, because let's say you've only.
So you divide. It's infinity up to different times.
Hawking photons that are going to come out, and then those can be entangled in. What's that?
The mass that arrives at infinity goes from.
You're talking about a process. Could you draw the set, the set of hypersurfaces on which I can imagine constructing a Hilbert space as a product of local Hilbert spaces?
Yeah.
So
yeah.
what is the set?
So
You're
take
discussing some time development, so you have some parameter, slicing parameter.
It's easier in Eddington Finkelstein.
Yeah.
I don't care.
Okay, it's okay. I mean, we can actually consider slices up here, which are all at a time when the black hole has completely evaporated.
Right, so there I have pure states.
And now I'm going to consider the Hawking radiation as it propagates on those slices. It's still propagating outward. Okay, I'm just trying to get away far from the black hole because I hope that will make you happy. And I can divide I can divide the slice into some part of the Hawking radiation. So I'm just going to draw some fixed size sphere here that is going to get crossed by this Hawking radiation. And I'm going to ask how much of the information is on this side of the sphere as a function of time. And so in the beginning there's none at all because none of the radiation has arrived yet. We're that far away. And then more and more of the radiation is on this side of the sphere. And eventually when all of the radiation is on this side of the sphere, then I think we're in agreement that I can read off the quantum state. Then it has to be pure. And so there has to, but it could be, you would expect that it's mixed and it's not, the information doesn't, it's not immediately there clearly because, so at some point, this information has to come out.
So, by the way, I think it's pure as long as it's a complete slice. Or if you
He's not looking at a complete slice. He's looking at part of the
backwards.
I'm looking only at part of it. Yeah.
He's looking at a subsystem.
What's the other part of the subsystem?
Do we have an ensemble or a single
What is the other part of the subsystem?
instance of these?
Remaining the black hole that still
There is no black hole. I mean, you really...
I imagine this is a particular pure state that I'm
Okay,
analyzing. that I
let's
send in
wait.
here.
Let's
But-
make a black
Are you doing the
Let's
measurement?
make a black hole and then let's wait.
You
Let's
prefer
go
the
back to
same
backwards.
Well,
state identically?
In order to really
And then we-
operationally check
that's what
unitarity, I would
Hawking
have to do
come
that.
out,
Right,
and
because
they're
you can't tell the
described by
difference between an
density
entangled state and a pure state with
And
You
no,
have to
the whole thing is
measure.
measurement
Measurement
they can be
You have to measure in different
with
ways.
the
Yeah,
stuff inside,
yeah.
which is the black
Okay.
hole that's still there and possibly other.
But I think that's an orthogonal. I mean, that's,
What is
we're going to do this.
slice goes
We can.
to?
We have high technology. We can make this
Yeah,
black hole
goes
over and
in-
over again.
black hole
No,
is
that's
like
fine. The thing is that in some sense,
you're-
since some of the things depend on how you entangle things
Yeah.
between both sides and the measurements that you've done before and after.
I mean, it's true that I cut a piece out, but if that is a problem, that would then you'd have to resort to basically remnants. I mean, you'd have to say that some of the information just never arrives at infinity, which kind of undermines the whole S matrix.
This picture is obviously wrong. We don't have singularities in the future inside the black hole.
Oh, here, this singularity.
Yes.
Well, yeah, maybe that gets
no
modified.
problem.
Right, maybe that gets modified. But how is that going to help? I mean, their argument is that there's a singularity right here. That's so. Okay, so we have to pick. The point here is that we either have to discover a hidden assumption that's going to unravel this, or a factor of 2 that they forgot, or we have to pick between these three. Between giving up one of these 3 things. So that's the choice that these
So
people
what's
are.
the one that's
So this wasn't this is the same situation as to whether we lose information.
It's all back to the it's terrible.
So
Except that now I think we have much better arguments for. I mean, back in whatever 1976 or even in 1993, I think the argument for unitarity was not yet as strong as it became after D-branes and ADS-CFT.
That was what Hawking gave up.
Yeah, exactly. That's what Hawking gave up. I think
No,
what,
he shouldn't have.
and of course the response
is obviously wrong.
the response of many people to this has been, Wald and Unruh and so on are going to say, I told you so, Unitarian. Okay, I'm not going to give this one up. Okay, I think most people in this room probably don't want to give this one up. Amps argued that the most conservative option was to give up the equivalence principle. At least to me, this is tantamount to giving up on the equivalence principle. If I can fall into an old black hole and essentially go splat on the horizon, no matter how big the black hole is, that's I think that undermines everything that the equivalence principle was about. In particular, it's not clear. I mean, normally, if you have such a violent thing as a singularity right at the horizon, you have to have some source for it. Then, of course, the equivalence principle argument wouldn't apply. You would have some Planckian shock wave here that would actually curve space. The equivalence principle is a statement about the vacuum, not about if there's stuff curving space. But it's not clear what that would be. The thing that's really happening, according to this argument, is that the vacuum rotted away. It broke. The thing that we want to have is not there, and instead what it's been replaced with is analogous to a pure state in Rindler space. If I pick a pure state out of a typical pure state out of the thermal ensemble in Rindler space, what I get is something that looks exactly like the vacuum until right here when I hit a singularity at the horizon. That's I think a close analog of what they find. So I'm not too happy about this. But unfortunately, so far I haven't found a way around it.
But, Raphael, in your way around, I mean, they're not arguing unitarity is not violated, right?
Sorry, that were too many no's.
Everyone here is accepting unitarity, or maybe Raphael will question.
No, I'm not going to. I'm not going
No,
to. I am not questioning unitarity.
Yeah, you're accepting unitarity.
I'm accepting unitarity. I don't want to touch that.
No, me too, myself.
I mean, yeah, sorry.
No, me too.
So this is the what to do list.
Haven't we already learned from ADS and CFT that this line of argument is just wrong?
Why?
Because you're not allowed to just write down a classical space-time and
No, but you still have to. It's a duality. It has to. The observers in the interior have to see.
I don't know what that means.
If semi-classical gravity and effective quantum field theory are not valid here,
What does interior mean?
then you have to explain to me what the range of validity of these theories is. This was supposed to be a regime in which effective field theory and semi-classical gravity are valid. If they're not valid here, then you have to explain to me what the...
One of the lessons of
Yeah.
ADS-CFT, is that the resolution of the unitarity issue, right, and the meaning of what black holes are is not something that is treatable perturbatively by making perturbatively around semi-classical gravity.
Previously, one might have thought the breakdown was only for correlations involving of order S photons. That was always the assumption.
Yeah.
It shows up in correlations involving 1 or 2 photons.
Yes.
Near the horizon.
Near the horizon.
All right.
But previously it was believed that you could fix, and maybe you still can, that you could fix this by
No, we can't.
No, the claim is that you can. The claim is, by this line of argument,
Oh, you
that
can
have
fix
to,
what?
Unitarity implies a breakdown of effective field theory. If it only applied a breakdown of effective field theory for of order measurements involving S quanta, okay, that's what was formerly believed. This is saying it involves breakdown of effective field theory even for observations of single quanta.
This is really great, actually, because I mean my key goal in life right now is to kill firewalls, and because I probably am not smart enough, is to convince other people to try as hard as they can to kill firewalls. And so that's,
Wouldn't it be better to just show they're there?
if you all come out of this
By the way,
fired up to kill firewalls, that would be great.
Let me ask a different
Yeah.
question, which is for those of you who are fans of eternal inflation,
Yes.
which I don't like another reason.
You don't like
Doesn't
data?
a similar thing happen in internal inflation? If you believe in internal inflation,
Yeah.
then the universe is always, any system is always in a mixed state because of all this stuff. You're entangled with going down to create these zillions of universes eternally.
Yeah.
And since we don't believe that's true, well, we want to preserve unitarity. Doesn't that mean there's a firewall?
Yeah, I think that if firewalls helped,
That's from internal
This
inflation.
might save,
right.
If this saves from eternal inflation, would you be happy?
yeah, I would certainly be happier about firewalls if they did something good for us.
happening all around us all the time.
I think the claim is that there's a democracy of horizons in the way we think about gravity, which is a Rindler horizon here or near a Schwarzschild black hole. It's the same in those situations. And what we're saying is not.
I love the discussion style, but
What we're saying is that it's not democratic, that not all horizons are
I'd like to make a few more points, and maybe we can defer the other comments until the
Well,
question
but there's
session.
also, there's another possibility in all of this. But it seems, these aren't questions; these are objections.
Not be deferred.
Yeah.
Anyway,
There are so many objections. Unfortunately, none of them seem to be very. But there's a couple of subtleties and points that I actually do want to raise, in addition to all the others that could be raised. One debate is, when does this behavior kick in? The argument that AMP's mate is sharpest if we consider a black hole after the page time, after half of it has evaporated. However, it's so it's open to discuss. We just don't know, I think, what happens before, even under, trying to apply the same logic, we just don't have the same kind of control because you have to start making assumptions about where the degrees of freedom are while the black hole is still large. The nice thing about the AMPS argument is that everything is in terms of field theory degrees of freedom that should be under control. This actually goes to the question about de Sitter space. De Sitter space horizons are thermal, but any quantum that's emitted on one side gets absorbed on the other side. So you're never in a situation where more than half of the horizon has somehow evaporated into a matter system that you could control with effective field theory and apply the AMPS argument in its strongest, most reliable form too. So again, I think there's a lot more room for speculation. And even if you do assume that a firewall forms after the scrambling time, which is sort of the earliest time that it could form, r log r, where r is the, let's call it rs, the Schwarzschild radius, we would not have reached that time yet in our universe. So it's not clear that there's any argument there. But eternal inflation could last longer. So
before you get to eternal inflation.
Yeah. No, I don't want to get to eternal inflation.
This argument, what does it mean, the breakdown? This is an observer at infinity deducing that a breakdown of...
good.
One second.
That's my next point. Yeah.
Observer at infinity deducing that a breakdown of effective field theory happens.
Yeah, and I drew this wrong.
His past, right? Her past. For quanta which have been blue shifted to arbitrarily high energies.
No.
Yes?
No. This is good. This was my first objection to their paper. I thought, this is great. This paper is wrong for the same reason that, well, not wrong, but resolved by complementarity. For the same reason that quantum Xeroxing is resolved by complementarity. Quantum Xeroxing problem, of course, is you have your pure state going into the black hole. You have your pure state out here in the Hawking radiation. You draw a slice like this. You have two copies when you started with one. No problem. Nobody can see both copies. You're either this guy or that guy. Nobody has them in a single passed light cone in that entire space-time. The problem here looks very similar. The infalling observer needs these guys to be entangled to be happy. The outside observer needs these two guys to be entangled to be happy unitarity-wise. Fine, we can just declare that since Alice cannot actually verify unitarity, she goes into the black hole. She doesn't have a chance to see the rest of the Hawking radiation arriving at infinity. So we can give her a theory in which these near horizon modes, inside and outside, are in fact entangled with each other. She just lives under the illusion of unitarity until she jumps in. This part of the radiation is consistent with unitarity, but then she miraculously gets free fall. And the reason that doesn't work, as I painfully learned by doing the corresponding thought experiment more carefully, is that the same thought experiment that works out for Xeroxing does not work out for this. The basic reason for that is that to get violations of Xeroxing, you really would have to see Planck scale physics near the horizon. To check this entanglement between B and R, Alice does not have to be at only Planck distance from the horizon. She can fall in, get into the near horizon zone, much further than Planck distance away from the horizon, be in free fall if she wants to, measure a lot of these modes, and then still decide that she didn't actually want to fall in at all and go back out without terribly large accelerations. And so she basically can decide to be Bob. Her theory has to say the same things about this entanglement that Bob's theory has. So then it doesn't matter whether she actually tries to measure this or not. That completely fixes the quantum state in her theory. And it's now I can't at the same time put B into entanglement with A.
Could you go through that again?
Yeah.
Alice, you're saying, could not be Alice, could be Bob.
Oh.
Is that what you're saying? Bob is only defined by...
No, so
what are you saying?
Complementarity, I can appeal to complementarity. I can say that Alice has a different theory that, for example, puts certain things into a different state. If she can't decide to go out anymore and become, if you don't have to have consistency with Bob.
Complementarity in the end
Yeah.
is a statement that, in effect, sort of the Hilbert space isn't HA cross HB, but it's HA or HB.
Yeah, yeah,
And
yeah.
either can evolve somehow from an H initial, which is what
Right.
we usually think of in this room.
Right.
Okay? It's
And to make that
I
consistent,
must
it's
say,
very
it's
important
not
that you can
much of
never
a
see
principle.
these Hilbert spaces that you're identifying. You must never see them as independent degrees of freedom.
So it's
right?
got so many questions associated with it because it was, just a statement, which obviously resolves the paradox, but it doesn't explain how one Hilbert space. That's why I wanted you to draw what you mean by the Hilbert space.
But these are field theory Hilbert spaces. So anyway, complementarity, even if I want to use it, doesn't help.
As I said, the way you usually define a Hilbert space in
Yeah.
field theory, or a small portion of the Hilbert space, most of the rest of which is totally inaccessible, is by a product of HX prime, HN,
Yeah.
And that's perfectly well defined back in the past initially, but on one of those slices there that passes through the horizon, it's rather confusing whether you are. And
No,
it
but
seems
this
to me
is
the
the-
principle of complementarity said there are two Hilbert spaces
Yeah.
which describe
Yeah.
the same system.
Well, so
And
this.
depending on whether you're Alice or Bob, you use one or the other. Now so there's an observer-dependent Hilbert space in this.
Right.
Which is fine.
That's another thing I
Although
tried.
the principle,
So you-
so-called of complementarity, never exactly explain
Yeah.
how this splitting would occur.
So the next thing you could
Now
try
you're
here.
saying your explanation of complementarity doesn't work for that very reason, because the observer, until they decide whether to turn on the rocket or not, could use either of these Hilbert spaces.
I mean, maybe the Hilbert space should depend on the trajectory, not just on the location of.
Oh yeah. Well,
right?
we can do
And Alice
that.
has no free will, which is common.
Oh, you mean on the future trajectory after she sees those modes? That would be problematic.
Or on the
Yeah.
global trajectory.
Then she has no free will. Yeah.
But in quantum mechanics, who has free will? If
Yeah,
you have free will, you lose
That's
unitarity.
good.
Yeah, we have something that's almost as good, which is, the ability to use an incredibly complicated algorithm to decide whether
Look,
to jump in or not.
to make a statement like the so-called principle of complementarity, which isn't much of a principle, is already a statement that you're going to use one description with one Hilbert space or another, right? Whereas the slices that Steve is talking about, use them both. And then you get into the problem. So you can make up any rule you want. It seems to me, based on intuition from ADS-CFT, you define initial conditions that will pick out the geometry for you, and you'll have one Hilbert space depending on the initial conditions, which, by the way, in a unitary theory, means there is no free will. Once you've got that state and the dynamics, the rest is determined, and you'll have the picture of the inside
If you want-
guy or the picture of the outside. No conflict. What's wrong with that?
So you want to use complementarity.
The initial state will determine
Whether Alice decides to
which
fall
you
in.
use. Period. You don't have free will to change that. Quantum mechanics.
That's a very interesting.
Let's
Okay.
give up unitarity.
So the state of the vacuum or not vacuum here will depend on some naively completely unrelated degrees of freedom down here, which are in Alice's brain. I mean, this is unbelievably non-local.
But
Look,
that's
if
what
that's
you
the
learned from
if that's the
ADS-CFT.
resolution, then it would be worth finding exactly how to implement it, what it would mean, because it's extremely radical.
Yeah.
Well, instead
Well,
of talking
it's the
about
only
free
thing that makes
will-
sense to me. That's what when I could never understand what this principle of complementarity meant, because it really means you have two possible Hilbert spaces,
Good.
not the direct
Yeah.
product of them.
Complementarity was not supposed to mean that you have to know at past infinity what Alice is going to do, but we could try to see if that would help. I think it's an extremely radical proposal, but then again, I don't like firewalls. So
Right. Part of this, the two measurements are similar to measuring the x component and the z component of a spin. And we know that we can't predict in advance that they'll both be up, because that,
Yeah.
Now you're telling me we could build into the laws of quantum mechanics that there's no free will So we know
We
what
know there
measurements are
is
going
no
to be
free
made.
will.
I mean, there's
Since
no-
We know there
since
is
there's no free will, we don't need, since there's no free will, we know the S component can be measured, so that we don't even need a theory of the Z component. That's what you're saying.
Yeah.
It's.
We could probably get rid of quantum mechanics.
But you can also avoid the question of free will altogether by saying there's both Alice
Yes.
and Bob. Alice and Bob both go towards the horizon. Alice falls in and Bob doesn't. No free will there. Both of them exist. And then the question is, the radical thing we would have to do is drop the idea that Alice and Bob agree on what's happening
Right.
before they've parted ways. If you can drop that assumption, that just seems so crazy.
I think that, you know, once you have the theory depend on Alice's brain state down here, it's not more radical to assume that something conspires to for them to communicate with each other here. I mean, both of these things are, you know, they would have to come from some deeper principle that would be completely obscured in the way we think about physics right now.
Well, yeah, the
that-
easier way, of course, is you know, you can impose, you calculate relative probabilities, you impose initial and final conditions. And, you know, which is, when you're loosely speaking in the way that you do, you talk about starting with infalling stuff, and now the observer at infinity. So you've already picked out a final condition, if you want.
No.
That there is an observer at infinity. Because for
It's
the
called an
Alice-
S matrix. You don't have to talk
for the
about a
Alice-
physical observer.
for the- Well, let's do it, because that focuses things.
If you want to do that, David,
And
you
then-
might as well just go for the black hole final state.
That's what I wanted to talk about, but unfortunately I don't have time.
That's what we. Well, yeah, so you
Yeah.
guys have a
So we
suggestion.
have-
I would love to talk about this, and I don't know if I can because I'm kind of, maybe
Well,
we should.
how about this? We'll give anyone who wants to leave a chance to leave
Yeah.
by
Yeah.
applauding.
Thanks for the forced applause. Oh, no. Yeah, so let me talk about, I got very excited about the final state proposals.
Good.
This is what Firewalls did to me.
Exciting.
And okay, I should say one more thing that I tried, it doesn't work so great, is of course you could try, in the spirit of what some people have said complementarity is, to say that the Hilbert space A is somehow secretly the same as some subspace of R, so that these two entanglements are really, you know, the same thing. I don't know how to make this work without violating linearity, because eventually R has to come back out here as A. If you have any ideas about how to make that happen, I'd be very excited.
Raphael,
Yeah.
a quick thing before the last diversion. You were mentioning the cosmological horizon. Now, with the horizon that produced, we think our initial fluctuations, RS actually is not so big, and so RS log RS actually, well, we would have firewalls in our past, I think.
Maybe we got lucky.
Anyway, just
it's a good question. Let me. Yeah. So let me discuss final state quantum mechanics. It's too bad that Jim Hartle isn't here. Basically, everything I'm talking about today, there are people here who know it far better. So again, I don't know why. So here's one way of saying what we do in quantum mechanics without a final state, and it's just a way of saying it which admits the most natural generalization, or the easiest one. So suppose I have some initial state, rho I, and I make a bunch of measurements each of which has outcomes. My notation is probably terrible, but I hope you get the. These don't have to be measurements of the same observable. They could be measurements of all sorts of different observables. And I just want to compute the probability of getting a particular sequence of outcomes. One way of computing that probability is like this. Just put the projection operators symmetrically around your initial state and take the trace, because each operator appears twice. Let's just consider the case where I make one measurement, and this is a pure state psi. I'm already squaring. It's all built in. So this is a probability for getting this particular sequence of outcomes. And the only thing that you have to do to get this crazy variation of the theory called final state quantum mechanics is you add some final state here. Again, it could be pure or mixed. And renormalize all probabilities. So what you can think of here is that you have your initial state, and you make a bunch of measurements. There are all these different possibilities of what might happen. And then if you don't get to your final state or something that's supported in the final state density matrix, you basically erase those paths. And then you have to recompute all the probabilities because you don't sum to 1 anymore. So you sum over all the paths. You see what they sum to. You divide by that. And Aharonov came up with this, I guess, with collaborators. Gell-Mann and Hartle pioneered this. What's not obvious in the way that I just explained it, but is obvious from the viewpoint of the trace, which is cyclic, is that this is completely symmetric with respect to initial and final state. I could have equally well started with a final state, drawn such a tree, and then post-selected on the initial on the initial state, and deleted some paths corresponding to the ones that don't end up with the right initial state, and gotten exactly the same answer. So it's very symmetric. But the viewpoint I think here is that there's the final state is somehow fundamentally built into the theory. So you shouldn't think of it as, I just make another measurement and I'm not interested in everything that happened before. If I don't get the right outcome, at least in the context that we're going to consider, it's built into the theory. And it's because you have to renormalize, it's not really linear. Okay, so much for the final state. Now let me just briefly review what quantum teleportation is. So suppose that we have Alice and Bob, and they share. They each get 1 bit out of an entangled EPR pair. So here's Alice, here's Bob, and here's some other system X. This is also a qubit. Of course, we can make this larger in Hilbert space dimension, but let's consider qubits. Some state psi, which Alice is trying to send to Bob, who's now far away. And the way Alice is going to do it is she's going to measure X and her bit in the entangled basis. So there's this basis 0, 0, plus 1, 1, 0, 0, minus 1, 1, 0, 1, plus 1, 0, 0, 1, minus 1, 0, with appropriate square roots of 2. She's gonna measure in this basis, okay? And so let's call these states phi sub I, with phi 0 being the one that this pair was in. She's gonna get some I, that's 0 to 3, and she's gonna send that information to Bob over here. And at this point, Bob can act with a unitary operation on his bit, depending on 1 out of 4 unitaries, depending on which message he got. This is a classical message, so she can just broadcast. And now he will have psi. This is an elementary calculation. It's easy to check. Now let's put these two things together. If I have final state quantum mechanics, I get to do one more thing, which is to insist that the state that I got here was phi 0. Okay, I'm just not interested in any other case. And in that case, if I know that the theory just says that, I don't have to send any information to Bob. He has the same theory. With phi 0, this is just the identity, and I don't have to do anything, and I've teleported the state for free. And that's the idea of Horowitz and Maldacena about 10 years ago. Just think of it like this. Here's the black hole. Here's the information coming out. So you get to have your cake and eat it. It's yeah. So you put a final state on the singularity, right? right? And you managed to get it out there, even though this is basically the vacuum entanglement. I mean, I didn't draw the picture completely correctly, but A and B here are really the same A and B more or less. Except if you want to think about the whole black hole, then B is now all of the radiation that ever goes out. So I'm just so I'm getting unitarity, but I'm also getting these two guys to be entangled with each other, which you need for infall. And in particular, because this is a pure quantum state, if I now divide B into two pieces like the early and late Hawking radiation, they can actually be entangled with each other. So I get to have double entanglement in these kinds of theories. This was pointed out particularly clearly, at least to me, by Kitaev and Preskal. And it leads to the following idea. Let's get rid of this contradiction by doing final state quantum mechanics. But if you check what actually happens, it's kind of annoying. Okay. One thing that you want to check, so let's check double entanglement. So, oh, by the way, the final state here for Horowitz-Maldacena is essentially the vacuum state. So it's constructed like the vacuum state for the matter and the in-modes, connecting them at the future singularity, and then no restriction on the B Hilbert on the state of B, and then you have to normalize this.
Your final state depends on the initial state.
No.
It's a canonical state.
This state here lives in a Hilbert space of matter cross A or X cross A. And so it connects every possible matter state with some state in the in-modes. It lives in the product Hilbert space of the matter that could have made the black hole, any matter that could have made this black hole, and the in-modes of that black hole. And it connects, so it really, yeah. Good. So the nice thing that happens, this is illegible anyway, so let me erase it. The nice thing that happens is if you calculate, I learned how to calculate this from Douglas Stanford, who learned it from Preskal. It's actually, well, if you don't know how to do it right, there's a fast way of doing it, otherwise it's very painful. So let this be the projection operator onto the state that I want by unitarity. I want the Hawking radiation. So I'm using the notation from here now. Hawking radiation has been broken up into two pieces. It should be in one particular state, the state that I sent in up to an S matrix. So I want the probability for this to be 1. Right? And yes, great. It's 1. Then let me ask whether you can fall through the horizon. So now I'm going to project onto the vacuum state at the horizon. So when behold, I get 1. So this is the magic of final state quantum mechanics. In this sense, you can have B entangled with two different other systems. But if you test for the right maximally, these could each be maximally entangled states, you always get probability 1 to get them. The problem is if you try to do both. And there's actually two problems. So let's suppose that I measure first, which Alice can do, right? She first measures BR. She checks that this outgoing radiation is in the correctly entangled state with the early Hawking radiation. And then she measures, she falls to the horizon there by checking whether BA is in the right state. The probability for this is 1 over n to the 4th, where n is the dimension of the Hilbert space, so basically e to the area over 4 to the 4th. So I guess 1 over e to the area. It's about as unlikely as it can. I mean, it's completely random. It's completely random, and this is bad for two reasons. It's bad because now you don't see the right state with very high probability. You don't see the right combination of entanglements since you dared to measure them both or check them both. And what's even worse, it's acausal. Because after all, the probability that the theory predicts for what you get for this test of VR depends on whether or not you later choose to measure BA. And that's bad. Okay? And it's worse in the sense that you can check that really any generic measurement of anything inside the black hole will spoil these predictions. And that should give us some hope, because we know about another problem with Horowitz-Maldacena that can be resolved, which is the Gottesman-Preskill objection. So let's see if we can reduce this problem to that old problem. So let me briefly discuss this. Okay. Let me go back to the quantum teleportation story, since it all comes down to that. If I have the same protocol as before, in fact, I'm going to post-select as well. But now I add, so here's my state psi, which I'm trying to teleport over there. Now I'm going to let the system X and the system A interact with each other before they get to the final state. In that case, as you can easily check, so there's some unitary operator UXA. In that case, it won't work anymore. Okay? But it's not a big problem, because you can simply redefine the final state. I mean, after all, if I put some unitary U dagger here that undoes what this unitary did, and then box the whole thing together and say, this is my final state. So I replace the final state with this one. Everything still works. Okay. Now, why does this help? Well, it should help, because after all, the problem has to do with measuring anything inside the black hole. And really what the problem is just as if you have an initial state and you do a projective measurement, you can basically wipe out all memory of that initial state. It's like that, or change it into a different one. So not surprisingly, if you have a final state and you do a measurement prior to it, that can also wipe out what that final state was going to do for you. Well, if the final state undoes all the measurements that are being done inside the black hole, after all, this is an interaction. Right? It's just, I mean, if I want to measure A, I have to throw a detector in there. That's matter. And then there's the A modes in there, which this is going to measure, so it has to interact with them. So this should fall under the same set of rules. Whatever saved Horowitz-Maldacena should apply here as well. What the detector measures gets unmeasured by the final state. And I think this works, but but the patient is dead. It works almost by definition. Now, but it's like the black hole interior wasn't even there in the story. Yes. And it's terrible. We're back at but more precisely, what is the problem? The problem is now that we have no way of defining probabilities for measurements inside the black hole. You can't do it by inserting projection operators into formulas like that. Because after all, the projection operators are just shorthand notations for, interactions with some environment that you trace over, you get decoherence, and so on. But right now, by definition, we've just said that we cannot do any such measurements inside the black hole. In fact, the black hole is the perfect box. There's no environment that anything can get out to. It's trapped everything. So the thing that you could try to do, and which I have tried to do, is to not compute probabilities this way, but just do it the old-fashioned way where you explicitly look at the state. You say, okay, there's going to be some effective environment for a detector. It's going to emit some soft photons or whatever that you get to trace over. Let's not think of projective measurements. Let's think of unitary evolution inside the black hole, and then tracing over degrees of freedom which are effectively inaccessible, and let's hope that we can. But it's not clear what state to use. Once I've signed up to final state quantum mechanics, I've given up my right to think about a particular state in between these projective measurements. And I can see that by just not having any projective measurements and just having an evolution from the initial to the final state, that these not be equal but also not orthogonal. What's the state here at 1/2 second, between 0 and 1 second? Everything is completely symmetric, so with equal right I can say it's F or it's I. So there's no... That's it. Thank you.
Talk just hit a firewall or something.
Jim Hartle has argued on other grounds that we shouldn't have a notion of a state at a moment of time in quantum gravity.
So who has argued?
Jim Hartle.
Ah.
Yeah, I mean, it's you know, you want to carry over certain
Yeah.
things, you know, a unitary S matrix, things that we could measure, but to keep the idea that you can have a well-defined state at every
Yeah.
Don't we know from ADS-CFT that that's wrong? That we can, the time after all goes over in the two dual descriptions, and there clearly are states on the usual quantum mechanical sense at a given time on the field theory side.
Although there's a lot of, it's only an asymptotic time, and there's a lot of ways of drawing
You
intermediate
could change the
surfaces.
gauge if you want. I mean, fool around, but
So
it seems that there is a.
There is a state at a moment of asymptotic time.
But Gary, what is it? The question is, how are you going to compute the probability for measurements inside the black hole? I'm happy to give up on the notion of a state, but what are we going to replace that with? We should certainly be able to compute the probability. If I throw in a detector and I probe the vacuum inside the black hole, I should be able to write down some formula. And I just don't know how to do it. I just don't know how to do it. Here, I mean, so when we're, if we're in the process of measuring quantum mechanics, here's another, modifying quantum mechanics, excuse me. Here's another crazy thing you could try to do. You could define some object sigma, which you could actually construct from your initial and final state in the following way. This is not a density matrix. Okay, this will not in general be self-adjoint. You can normalize the trace to 1, but you can. So this is the product of the initial and the final state. What it basically will be is this.
It's a direct product or a product?
Yeah, it's a direct product.
So it's not.
Sorry, no, a matrix product. So yeah. So this is, this is not something you can normally compute probabilities from because it's not self-adjoint. However, you might argue or try to argue that an infalling observer will at all times only see certain subsystems, such that if you do a partial trace of this object over the complement of those subsystems, you do get a good density matrix. I'm not yet completely convinced that this doesn't work, but it certainly is the construction of this is not in general how this object would have to be constructed, and the construction of it is quite nonlinear. So it's okay. It's very hard to get rid of firewalls. You could, yeah. These are the nuclear options, and not even they seem to work. But Steve, handing over.